more work on our functions that we've been going through. We're going to talk a little bit more about domain and range just briefly, and then we're going to go through and talk about our parent functions. So remember, when we talk about the domain of a function, we're talking about the legal input values that we can put into the function, and that is always our horizontal axis. The domain is always our horizontal axis, regardless of what variable they choose to call the domain. So here are all of our input values that lead to output values, our y values that we have along the y-axis. So there are our range values. Again, regardless of what variable they use, if we're in the xy plane, then all points on this graph have coordinates, horizontal coordinates x, and vertical coordinates y. So all of our domain values are what we put into our function machine, and all of our range values are what come out as a result. So let's look at this function. This says to use a graphing calculator. We don't need to. We can draw this function, or we'll look at a graph of it in a minute. So let's just talk about what are we going to get in trouble with in domain values for this function. So we're going to get in trouble because this is an even root, a square root, when whatever is underneath there yields us a negative value, because that puts us in the complex range or in the complex plane, not in the real plane. And we definitely want to be in the real plane. So we're not interested in anything that would give us a negative output. So we're just going to pull out from underneath that even root what the manipulation is on our independent variable, and we're going to see for what values of x are we going to be in this situation. Are we going to have negative outputs? So we're going to solve this using good algebra. We're going to solve this for x. Now I'm going to divide both sides by -1. Remember that flips my inequality sign. So this is going to happen when x squared is greater than 4. So if I square root both sides, that's going to be, we have to be careful here, a plus or minus 4. So anything that we could square that would give us a value greater than 4 is going to cause us to be in trouble. So all of the values outside of 4 and -4, we're okay at -4. Sorry, my bad. Slow down. Plus or minus 2. If you were freaking out, I apologize. I'm paying attention to my signs and not paying attention to my value. So x can't be greater than or equal to plus or minus 2. So we're okay at -2. 4 minus a -2 squared is 0. We're okay for all values in between -2 and +2. For instance, if I put 1 in there, I'm perfectly okay. That gives me a positive value. But if I try to put -3 in there or +3 in there, we'll go down here. We'll put in -3 and square it. That's 4 minus 9. That is a -5. I'm going to be in trouble. So here is the domain of this function. There's the domain of the function. So I want to pay attention to, and I look for, again, values that I have to throw out. And the ones that I have to throw out are the ones that I know will not be in my domain. So let's talk about the range, and in doing that we need to look at the graph. So if we graph this function, it actually looks like the top part of a circle. And we can see that we were right about that. Our domain values are -2 to 2, inclusive of the endpoints. We can see along the y-axis that the range of our function is going to be all values from 0 to 2, again, including the endpoints. We will get 0 out of there, and we will get a +2 out of there. So our domain values are all values that it's legal for us to put in there where we don't have a negative under the root sign, and our range values are all values that will come as a result of evaluating that function rule that we have. So domain, pretty easy to find, pretty straightforward. You got to worry about a negative under an even root or division by 0. Everything else is legal for us in mathematics. Range right now, pretty much just going to have to look at the graph. So let's go here, and not really sure why this is acting that way. Don't understand this at all. Let's try that. There we go. All right, now let's talk about increasing and decreasing functions. So we know that a function is increasing when we compare one point to another point on that function. If we make a comparison and the output of the function to the right, we'll call it, I don't know, a to the right. If that output is higher than the output was at a, if the output of the function a little bit to the right of a is bigger than the output of the function at a, that is the definition of an increasing function. For decreasing, not surprisingly, we're going to do the same thing. Let's look at the output of the function at b, and let's compare it to the output of the function at c. And for decreasing, if those outputs, if that output at that one input value is greater than the output at this other input value, then we know that the function is decreasing. So we have to have 2 points for comparison. If we're going to compare what's happening to our function as we always move from left to right, we're looking for increasing or decreasing behavior by comparing what's going on our function looking left to right always. That's what it means to be increasing or decreasing. So that's just a straightforward definition of how we're going to compare. So we have to have, and this is just symbol notation, if we look at any arbitrary input value and compare its output value with another value to the right, looking left to right, if we compare those output values and the output value on the rightmost point is bigger than the output value to the left, that is the definition of increasing. Again, if we look at input values and their corresponding output values, and as we go from left to right, if the comparison is that the rightmost output value is smaller than the one to the left of it, that is the definition for decreasing. So we look for intervals over which a function might be increasing or decreasing. And those intervals change whenever we have a hill or a valley. So this function is increasing for all input values over this interval. It looks roughly like from -4 to -2. And then it changes to decreasing. So this function is increasing over this interval, and by definition we can see that it's decreasing over this interval, and then the outputs looking left to right start increasing again over this interval. So this is increasing, and then from this interval the function is decreasing. So we usually get asked, for what domain values does a function have a certain behavior? So if we were asked over what input values, over what x values is this function increasing, this function appears to be increasing, and I'm just going to put from what I can see on here. This may well go on off here, but we're going to pretend like it stops right there. We'll pretend like this one stops right there. So we definitely know from -4 to -2 this function is increasing. It's also increasing from 0 up to 1, 2, 3, up to 4. So a union of two sets. So this is the interval over which this function is increasing. If we were to look at the interval over which it was decreasing, that happens from -2 to 0 and also happens from 4 to 6. So if you are doing increasing, decreasing work and you're looking for the interval over which that's happening, we're always talking about X values. It's always going to be domain values that you show, unless it specifically asks for output values. But when we talk about increasing, decreasing, we're talking about the domain values over which the function exhibits that behavior. So when we have these changes, these hills and these valleys, we have what are called local maximum and minimum values of the function. The hills and valleys where the behavior of the function changes are what we call local maximums and minimums, not global ones. Global is the overall highest output value or the overall lowest output value of the function on its entire domain. We're talking about little hills and valleys all along the function. So if we're looking for a local maximum, then we're looking for where the outputs of the function change from increasing to decreasing. So we can tell when we have a change of increasing to decreasing, we had a local max or a local min. And specifically, if we change from increasing to decreasing, we know that it was a maximum. If we change from decreasing to increasing, we know that it was a minimum, and so forth. So we go increasing to decreasing, that's a maximum. Decreasing to increasing, that's a minimum. And that happens at one and only one domain value. So we can locate maximums and minimums at an input value, at an X value, but we can also, since it's just one point, identify the corresponding Y values that go with it. So if we came back up here to the example that we just used, we could see that here at -2, we went from increasing to decreasing. We have a local maximum at x equal -2, a local minimum at x equals 0, a local maximum at x equal 4, and a local minimum at x equal, well, no, we don't have, sorry, we don't know for sure what we have there because it's not a hill or a valley. Okay, so again, if we're talking about increasing or decreasing, when we go from increasing to decreasing, that's a local maximum. When we go from decreasing to increasing, that's a local min. Here we have another local max, and here we have another local min. Now the one thing I want to point out is we can talk about the X values. X values are given where. It gives us a location of where the max or min occurs. But I want to point something out. The Y values, the range values, are the max and min values. So if I gave you the graph of this function and I said, what's happening at x equal -3, you would tell me that this function has a local max of +2. So the Y value is the value of the maximum or the minimum. Here we have a local min of -3, a local max of +1, a local min of -1. Even though we can state what X values they happen at, the max and min values themselves are range values, output values. So let's move forward and let's talk about parent functions. There are a handful of functions that we call parent functions that you need to know how to graph. You need to know all of their behavior, what their domains are, what their ranges are, if they have maxes, if they have mins, if they have symmetry. Parent functions play a big role for us. So the first parent function we're going to talk about is the parent linear function. Well, that just went really quickly, didn't it? There we go. We're about at the end of this video. I think I'm going to go ahead and stop it here. So look for the next video and we'll go through our parent functions.